Hello students, welcome to the lecture. So students, as we know that we are covering the modern physics and this is going to be our part 5. So far we have completed the parts 4. Now we are going to start with the part 5. I hope you have revised the previous parts in the well enough manner before you have come for this part because it is essential for you that you revise the previous one. As we have seen in the previous parts also, that the topics that we are covering in different parts, all these topics are actually interconnecting with each other. So if you missing one topic, you will not be able to understand the another one. Okay? So that's why it is necessary just not only watching the lecture but revising the facts and figures on the regular basis so that you could make up yourself to connect with the upcoming topics. So here in this lecture, we are going to talk about the stellar energy, control thermonuclear fusion, nuclear holocaust, radiation hazards, India's atomic energy program. So these 5 things we are going to cover over here, starting with the stellar energy, control thermonuclear fusion, nuclear holocaust, radiation hazards, India's atomic energy program. Okay, but before starting, there is a small disclaimer that we are required to understood before we proceed further. The disclaimer is like the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. So here we are going to start with the first topic, that is the stellar energy. From the study of the sun and the stars, the most abundant nucleus in them is that of hydrogen, therefore the proton. So when we talk about the sun stars, which are the heavenly body and also the you can say lubricant body, not luminous, sorry, not lubricant, luminous bodies. Okay, why? Because they are having their own light. Okay, they are not non-luminous that they are dependent on another body for the lights. They are luminous because they have their own light. So basically, when we study them, sun and stars, what we found is that the most abundant nucleus that present in them is actually the hydrogen, therefore the proton. We postulated that the interior of the sun and the stars provide conditions for the fusion of hydrogen nuclei to form helium nuclei. Like in the previous lecture, we had discussed it. There are two types of nuclear reactions. First is nuclear fission, second one is nuclear fusion. For nuclear fission, we actually break down a heavy nucleus into the smaller nuclei. Okay, this is the nuclear fission. For nuclear fusion, just a reversible case. Like there are the two nucleus and we combine them to form a heavy nucleus. Okay, so this is just a basic difference between the nuclear fission and the nuclear fission. So basically, in the sun and the stars, because the hydrogen nuclei is actually in the abundance, so that's why the fusion of hydrogen into helium happens on them. Okay, so in the nuclear fusion that actually going on suns and star, there the hydrogen is getting changed into the helium. In this process, the mass defect delta M appears in the form of radiant energy, capital E, that is according to the relation E equals to delta mc square. Okay. Simple calculation shows that the sun loses 4 into 10 power 9 kg of its mass every second in this nuclear fusion. If we take mass of the sun as 2 into 10 power 30 kg, the sun would continue to radiate energy for another 30 billion years. So we know in the conversion of this particular nuclear fission reaction and even in the nuclear fission reaction, there is a slight change in the mass of products in comparison with the mass of reactants because some of the mass got lost. Okay, so similar case if we apply there and we do a study about it, what we actually found that the sun is losing 4 into 10's power 9 kg of its mass every second. And if we take this into account and we assume the mass of the sun is nearly about 2 into 10's power 30 kg, then if the sun loses the 4 into 10's power 9 kg mass every second, then it could be able to radiate energy for another 30 billion years only. Then what will happen to sun after that? By that time, the sun core will be largely helium because the hydrogen will convert it into helium and it will begin to cool and the sun will start to collapse under its own gravity. The sun is right now a hottest object we know in our solar system. We are not including the stars right now. What we are talking about only the solar system where we have sun at the center and the 8 planets revolving around it. Okay. In some of the cases we call 9 planets. Why? Because we take the case of Pluto also in it. But actually in September 2006, the Pluto was declared as the dwarf planet. Okay. And that's why it is now not included in the group of solar system, or you can say the group of 8 planets. Okay, so basically in solar system we have sun at the center and 8 planets revolving around us. That's it. So basically after 30 billion years the sun core will be largely helium and then it will begin to cool and the sun will start collapsing under its own gravity. Thereafter, this will raise the core temperature and cause the outer envelope to expand, turning the sun into the red giant. The two types of thermonuclear reactions have been postulated in the stars for fusion of 4 hydrogen nuclei to form a helium nucleus, along with the emission of a huge amount of energy. These are, first is proton-proton cycle, PP cycle we often call it, carbon nitrogen cycle, CN cycle. Okay, so these two cycles are actually the thermonuclear reactions that happens in the star where the 4 hydrogen nuclei converts into the 1 helium nucleus. Okay, and the emission of huge amount of energy takes place. First cycle, proton-proton cycle, PP cycle. Second cycle, carbon nitrogen cycle, CN cycle. These two. Okay. In the sun, both the proton-proton cycle and the carbon-nitrogen cycles occur with equal probabilities. It does not mean that the proton-proton cycle will have higher rate over the carbon-nitrogen cycle or carbon-nitrogen cycle will have the higher rate on proton cycle. That is not going to happen. They both will happen on the equal probabilities. In stars whose inter temperature are less than that of sun, proton-proton cycle dominates the energy generation. Again, in stars whose inter-temperature are more than that of the sun, the energy generation is mainly due to the carbon-nitrogen cycle. Note, nuclear fission is the solar stellar energy. So remember when we talk about sun, so both the proton-proton cycle and the carbon-nitrogen cycle, they happen with equal probabilities. When we talk about the stars, there are the two conditions. For proton-proton cycle, actually the inter-temperature must be less than that of the sun. Then the proton-proton cycle will dominate the energy generation. Second, in the case of stars, if the interior temperature more than that of sun, then carbon-nitrogen cycle will take place. Okay. In stars, this is not for the equal probabilities. It depends upon the inter-temperature in comparison with the sun. If lower, proton-proton cycle. If larger, carbon-nitrogen cycle. And nuclear fission is actually the source of stellar energy. Now, controlled thermonuclear fusion. The controlled thermonuclear fission is actually the basis of fusion reactor, which is the future source of unlimited and unpolluted energy. The most attractive reaction for terrestrial use are 1H2 plus 1H2 equals to 2He3 plus N plus 3.2 MeV. 1H2 plus 1H2 equals to 1H3 plus 1H1 plus 4.03 MeV. 1H2 plus 1He3 equals to 2He4 plus N plus 17.59 MeV. Deuterium, the source of deuterons for this reaction, is available in unlimited quantity in seawater. Other requirements for fusion reactor are: first is the high particle density. The deuteron-deuteron collision rate could be high only when the density, that is the number of interacting particles, is very large. Then we could go with the deuteron-deuteron collision rate. At high temperature requirement, deuterium will be completed ionized, forming the neutral plasma. A high plasma temperature of the order of 10 power 9 K or Kelvin is required so that interacting particles could penetrate the Coulomb barrier and fuse together. Second condition is a long confinement time. The hot plasma must be maintained at a sufficiently high density and temperature for a sufficiently long time so that the fusion of enough fuel occurs. No solid container could withstand these conditions. Therefore, clever confining techniques such as magnetic confinement and inertial confinement are being explored. Efforts are being made all the world over to achieve the controlled thermonuclear reaction in the laboratory for this purpose. Now, nuclear holocaust. What do we mean by this? Let's have a look on this. Nuclear holocaust is the name which is given to the large-scale destruction and devastation that would be caused by the use of nuclear weapons. In the fission of a single nucleus of 92U25, about 200 MeV energy is released instantly in 10 power minus 9s. If each nucleus in about 50 kg of U25 were to undergo fission, total energy released would be 4 into 10 power 15 joule. This is equivalent to the energy from about 2000 tons of TNT. Such an uncontrolled release of enormous amount of nuclear energy is what we call as an atomic explosion. Because it is uncontrolled means that it is not a controllable nuclear reaction. It is actually that particular amount of energy releasement of nuclear character that we couldn't control in a way we want it to be. So it is totally uncontrolled and we don't even know when it will stop and how it could be controlled. It is the enormous amount of nuclear energy, and that is what we called as atomic explosion. First such explosion occurred on 6 August 1945 when the United States of America, in short USA, dropped an atomic bomb codenamed Little Boy on Hiroshima in Japan. This resulted in the killing of 66,000 persons and injury to 69,000 persons. About 67% of city structures smashed. So if we talk about this, we could say in the time period of 1939 to 1945, the Second World War was going on. During that time, Japan and America entered into the state of anonymity, and during this course, the USA used the first and last reported incident in world of nuclear weapon usage. Okay, they dropped the atomic bomb that they called as a little boy on Hiroshima, the city in Japan. And this bomb caused the death to 66,000 person and injured 69,000 person. About 67% of the city structures got smashed. In the second attempt, the second atomic bomb that codenamed Fat Man got dropped on Nagasaki in Japan. This was more complex in comparison to first, therefore the little boy. Another nuclear accident occurred in 1986 in USSR, resulting in huge devastation that is known as the Chernobyl disaster. The radioactive waste will hang like a cloud in the Earth's atmosphere and absorbs the sun's radiation, and there may be a long nuclear winter. So basically, the two main important nuclear disasters that we have in the history of humankind on this earth. First is when the USA dropped the nuclear weapons or nuclear bombs actually, that is also called as an atom bomb, on the Japan. Two cities, Nagasaki and Hiroshima, got targeted. Second incident, that is the incident of 1986 and USSR. So basically, when the USSR was united and not got divided, there was a place called Pripyat. Okay, in Pripyat, the USSR established a Chernobyl nuclear reactor. During the, you can say, common safety test, the Chernobyl nuclear reactor, one of the reactor got blasted. And because of this blast, the high amount of radiation spread all over the city, and that caused a huge devastation. And still today, no one is able to live in the city of Pripyat or Chernobyl. Got it? Then the radiation hazards. Radiation hazards are harmful effects on an organism caused by the radiations. We know that high energy nuclear particles and gamma rays ionize a material through which they pass. Therefore, when an organism is exposed to the nuclear radiations, ionization of its atoms may break up the complex organic molecules and the normal functioning of biological system may be disrupted. Okay, so basically, why the radiations or nuclear radiation are harmful, having the harmful effects on the organisms? Because we know that whatever way they penetrates, they actually ionize the material, right? So the high energy nuclear particles and the gamma rays actually ionizing the materials through which they getting passed. Therefore, if there is any organism that got exposed to the nuclear radiations, the ionization of the nuclear atoms may break up the complex organic molecular system that is in the organism, and that's how his biological system may be disrupted. For example, if we talk about the Chernobyl disaster, in the Chernobyl disaster, the firemen who were trying to prevent that fire that was, you can say, spreading in the plant, okay, they had no idea like whom they are going to mess with, and they got exposed to the nuclear radiations that resulted in their painful death. Their DNA configuration got changed, their skin start melting and coming down of their body, and their body got swelled, and then they got died. So that's how you can say that the biological system may be disrupted up to that extent that you can't even imagine. So if you and anybody got exposed to the hazardous nuclear reactions and the radiations, you may not feel the immediate impact. But with the passage of time, your body will start disruptions, and that may cause death also. The damage would depend upon dose of radiations, rate of dose given, nature of the organism exposed. The dose of radiation is actually measured in terms of Roentgen R, which is the quantity of radiations that produces 1.61 into 10 power 12 pairs of ions in 1 gram of air. 1000 of 1 Roentgen is a milliroentgen. These units are what we call exposure units or dosage units. Like if you have to tell me like what is the intensity of exposure. Okay, so how you could use this unit to tell me that if this is having that much of rotation, it means that he got that much exposed to the radiations. They do not depend upon time. That's why you not feel the immediate impact. The radiation absorbed per unit time is what we call the exposure rate or dosage rate or radiation absorbed rate. The harmful effects of radiation on human beings could be of two types. First is pathological effect. Second is genetical effect. A radiation dose of 100 R may cause cancer also. The dose exceeding 600 R cause almost immediate death of the organism because the entire biological system will get fail immediately. The safe limit of exposure to radiation over the entire body is put at 250 milliroentgen per week. This is what we call permissible dose. When the radiation passes through genetic cells, there occur mutations of the chromosomes of the cellular nuclei. The mutations transmitted from one generation to the next and so on. Genetic effects are irreversible. The safe limit of radiation exposure as regards the genetic damage is not yet precisely known. Now, let's have a discussion about the India's atomic energy program. So, the atomic energy program of our country was launched around 1950 under the leadership of Homi Jahangir Bhabha. Okay. The major milestones achieved so far are first nuclear reactor that we named Apsara went critical on August 4, 1956. It used enriched uranium as fuel and water as moderator. Another reactor that we named Canada-India Reactor, CIRRUS, became operative in 1960. It is used natural uranium as fuel and heavy water as moderator. Research reactors like Zarlina, Purnima, Dhruva and Kamini were commissioned later. The last one that we use is U-233 as a fuel. The fast breeder reactors which use plutonium-239 as a fuel do not need moderators. They could be used to produce fissile uranium-233 from thorium-232 and to build power reactors based on them. Fifth, we have mastered the complex technologies of mineral exploration, mining, fuel fabrications, heavy water production, fuel reprocessing, etc. Elaborate safety measures, both in the design and operation of reactors, strongest standards of radiological production are most important hallmarks of Indian atomic energy program. So, with this, we have finished this particular lecture. Now it is advisable and requestable to all of you. Kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.